we're going to be doing, so first going to go through a bit of a preamble, and let's get in on this, okay? So before anything, I like to make sure you have an idea of what exactly we're talking about today versus what we're not talking about today. So I'm going to be focusing in on a key tool, a mathematical tool that we use for describing complexity for algorithms. So what's complexity? These are the resources, the amount of resources needed to solve a problem with an algorithm. So I thought I would give you an idea of just where exactly we are in this process. So usually when you study a problem, normally when you're using some model of computation to measure how many instructions or how many operations are happening for your given algorithm, you perform these kind of key processes. So usually the first thing you do is you present an algorithm. Now keep in mind that this algorithm may be correct or incorrect. So we're not going to be talking about this. So remember that an algorithm may or may not be correct. That's not what I'm going to talk about here with you today. Today I'm going to be focusing in on a specific part of this. So once you have an algorithm, normally you would like to analyze it. So for example, proving its correctness, meaning that we can guarantee that whenever you give it input, it always produces the correct output. So usually the next step after this is you try to analyze its complexity. Remember, like I said, that is the amount of resources that the algorithm needs to perform the computation. So usually people measure things such as space complexity, so how much memory gets used by the algorithm. You may talk about time complexity. That's a very common one, the amount of time it takes. Normally this is measured in operations based on what you're using as your model of computation. So people use, for example, the random access machine model. Some people use Turing machines to do this. I'm going to focus I'm not really talking so much about that here, but the point is that you decide on some analyses. So you just decide on a type of analysis. So once you have kind of a model that you're analyzing the algorithm, keep in mind, normally you develop the algorithm for the model. So if we're talking about general purpose computer models of computation, then that would have been done in step one, because you have to describe the algorithm in a way that is understandable or translatable to such a model. So when you're determining the type of analysis, people measure the complexity in all sorts of different ways. For example, worst case, average case, best case. When they do this, what they do is they count up the number of operations that happen in a particular way based on this model. So once you've done this, when you count up these operations, you derive something we call a complexity function. So you derive a complexity function. For the algorithm's analysis. So that's the third step. Now, notice that if you do this well, then it will reflect the complexity for the given algorithm. Now, like I said, this entire process is, okay, I give you an algorithm, I do some type of analysis, I decide on the analysis, what I want to investigate about the algorithm, or which gives us some insight into the problem, usually. And of course, we derive this complexity function. So this complexity function measures the complexity for a given size of the input. And then naturally from here to this last step is to determine what we call the asymptotic behavior of complexity function. So this is step 4. Normally this is expressed in what we call the Big-O notation. But there's other kinds of asymptotic notations. Now, what we're going to focus on is right here. So we're going to be presuming we're given some complexity function that measures the complexity of some hypothetical algorithm. And then we want to determine its asymptotic behavior. So normally we would like to have some complexity function. I would like to prove its Big-O, which we're going to talk about what that is today. So we're going to look at where this the squiggly arrow, I thought it was a little fun to make it squiggly. What exactly happens here? So that's what we're going to focus on here today. And that's what the focus of the Big-Oh Bootcamp is what exactly do we do? Like, so how can we prove that we have a given complexity function? How do we prove to somebody that it has a given asymptotic behavior? So for example, if I give you some function like big O, like say if it's like n, I want to show you that it's what we call big O of n. But I would need some rigor to do this. I can't just simply just assert it to you and you just kind of say, trust me, bro, it works like that. That's not how this goes down normally if you're dealing with formalisms here. So that brings me to defining a couple things. So first, hopefully this is going okay so far. So just remember, this is kind of like where we're at. So we're just going to look at that one step. All of this would be a complete picture for an analysis of algorithms class. But I'm going to focus only on this step because usually students have difficulties focusing in on this step. But at the same time, it gives you some insight on how you can measure growth of a given function, but also how you can think about a whole class of functions and see how they're interrelated as the input gets large. So they belong in these little bubbles or buckets, as we're going to see. So another thing I need to define for you is something called a complexity function. So you know how I talked about this idea of deriving a complexity function? I got to define that for you. So there's going to be a definition I'm going to use. This is our working definition for a complexity function. Remember, this measures the complexity of the algorithm, the resources that algorithm needs to perform the calculation or the computation. So let me give you a definition for this one. So it's going to be what we call a function f on the domain. So don't worry, I'm going to draw you a fun picture. I am a big fan of fun pictures. On the domain of positive integers, to non-negative real numbers. So for those that really like so-called mapping notation for functions, what I'm telling you is that this function takes as input a positive integer, and as output, it spits out a non-negative real number. So these are real numbers that are 0 or larger. So just as a reminder what a function is, I like to draw it in terms, I like to think of it like a machine. So imagine you have this funky machine. I don't know what this function, it looks funny. So what it does, it takes an input in the top of it, and it spits out a result that the machine will compute. Goes through some process. I don't know what it is. Whatever the complexity function is defined to do. So in this case, what it does is it takes in a positive integer. That's what this fancy Blackboard Z with the plus means. It means positive integer. If it doesn't have this plus, it means it's just an integer. So these are numbers like -2, -1, 5, 7, and 0. Those are integers. Positive integers only includes 1, 2, 3, 4, 5, your typical counting numbers. This is in contrast to non-negative integers. These are 0, 1, 2, 3. It includes 0 in there. So I put an integer in, function f, that's its name, will then perform some calculation, and as output, it produces me, like say if this is n, so suppose I called that n, the input n, it spits out f of n, which this right here is a non-negative real number. So that means that we're talking about numbers like 0, 1/2, pi, things like that. So this is what we're going to refer to as a complexity function, but I must stress, as a convenience, sometimes I'll define the domain, meaning that's what our inputs for this function are. I'm going to sometimes allow it to have the value 0, even though it doesn't make a whole lot of sense from the standpoint of the input of an algorithm. Sometimes it actually does. So if you think about it as like, oh, the size of the input, okay, well, what if I give you no input? Now, typically when you don't have any input, there's nothing really to compute, right? But the thing is that sometimes I would like to express the complexity function in terms of itself, what we call recursively. And sometimes it's helpful to have the ability to define it for the input when it's 0. Theoretically speaking, it doesn't make any difference from a big O standpoint, but it just simply is a convenience I'll be using, not today, but some point in the future. So are there any questions about this? Does this seem pretty darn clear? So just as an example, a complexity function can be something as simple as like f of n is n. You can also have other functions like this. Like you can have what we call a constant function. Say f of n is 5. And keep in mind that the name f isn't special. You can call it something else like g. So I can have g. I can make this n squared plus n. So just keep in mind that f there is the name of the function. But very often when I write this out, I'll be specifying its input here. Although technically speaking, the output of the function is called f of n, I'll usually be writing this out regardless, just to keep it easy so you can see what the input is. It's a shorthand, but it is an abuse of notation. So I must stress that there are other ways you can define what we're going to call the big O notation. For example, it uses something like using absolute values and things like that. I'm not going to focus on that definition here because it's not really going to add too much for us from a computer science I'm getting very excited here. A computer science standpoint, it doesn't really add anything for us. Because keep in mind, a program cannot perform negative number of operations, okay? It's not like the computer, you're like owing the computer an operation. So you can imagine like a computer program that performs operations for some sized input. It performs some operations. It doesn't have the ability to just perform negative operations. It's just a convenience when you want to talk about general functions. And that's why some people define it like that. I will not be doing that here. It doesn't really add a whole lot given the fact that most complexity functions that you actually study in computer science do not really need that. Because most complexity functions you're going to run into have a very specific structure to them. Including the fact that they're programs and they perform operations. And when I count those operations, they're always going to end up being some non-negative number. So a program that does nothing, for example, which is very strange, by the way, to imagine. That, for example, performs 0 operations, but such a program is very hard to conceive of. If you think of it like, okay, the program still has some operation it has to do. It has to obviously tell you to stop computing, right? Well, that's still an operation, right? It's kind of weird to think about. But you can think in a theoretical sense of such a thing existing. So anyways, it's also a convenience for us because some of the functions that we're going to look at have it where they spit out for the smallest inputs the value 0. For example, logarithms have such a thing. So for example, log base 2 of 1 is 0. So that's also another reason why I've restricted the definition like this. It's very common in computer science circles. So are there any questions out there? Don't be shy. I'm really happy to answer any questions. So far we're doing okay? Okay. So let's proceed. I'm going to now talk about the definition of big O. And I'm hoping that I'll be able to give you some idea of what this definition is. Awesome. No, good. So we're going to be heading over here, and we're going to be talking about the definition of big O. And I must stress that big O is very commonly used in algorithm analysis. And when people talk about different algorithms, they usually talk about the running times in terms of big O notation. So this is also for several other reasons that I won't go into so much here, but the point is that regardless of the implementation of the algorithm, you can find out when you count up the operations that are performed, it always falls into some bucket of functions. And the big O is effective at capturing this. So yeah, I'll give you some insight into this as we go along, but it's not really the focus here. So I'm going to first talk about the definition of big O, because it's probably a good place to start. Now, I must stress that this notation is something that birthed more out of analytics from mathematical analysis. So it was not primarily developed for algorithm analysis. This is something that came along later. So sometimes people refer to Big O notation as Landau symbol, named after one of the mathematicians that popularized this notation. But I must stress that its definition did evolve over time with Donald Knuth and others of the sort. But anyways, it's a kind of what we call asymptotic notation. As the name suggests, it means that the input as it gets big. So you think of it as things get big, this is what you would expect the function to behave like. That's how you could think of what I mean asymptotic, as it gets large. But keep in mind it has a double meaning in the world of computer science. For example, like I said, you could think about as the scaling of how well the algorithm scales. So for example, if you have very large inputs, like say for example, your algorithm is computing on an array, like if it has only 10 things it has in this array versus 10 million, it makes a big difference if you have a very slow algorithm versus a rather fast one. I'm not going to talk too much about fast versus slow here, but you can get an intuition that the Big O notation will be helpful for discerning a fast algorithm from a slow algorithm if you wanted to compare two different algorithms when the array, for example, is 10 million elements as opposed to just 10. But also, another reason why is because it captures all of the inputs for a given problem at the same time. That's another reason why the Big O notation is helpful. You can think of it like just a nugget that you could present to somebody and say, this is the complexity of the algorithm right here. And I could describe it in terms of the input size. So that's the way I usually like to prefer talking about it. So I'm going to define, so when we talk about what a complexity function is, I'm going to let f and g, in the truest way of some sort of thing like this, I'm going to let them be called f and g. They're going to be complexity functions. And I assure you I'm going to draw some pictures and have some fun demonstrations here shortly. So let's get in on here. So be complexity functions. So when I write f is Big O of g, this is equivalent to me writing the following. Now, very often in logic, we'll say this is if and only if. So that means that if I say that f is Big O of g, it must be that whatever follows after this if and only if also has to be true. If f is not Big O of g, then whatever follows after this if and only if isn't true as well. So that's how you just need to think about when we talk about this. They're equivalent statements. That's what I'm trying to tell you. Is that if this is true, then this has to be true. If that's false, then this has to be false. Okay. So let's talk about this. So if and only if there exists. So you're going to see that I'm going to describe this in a way that's also going to sound like a game of sort, that we're going to try to figure out some of these interesting numbers here. So watch. There exist positive real constant. So this is a positive real number. So positive real constant C. So we're going to call it C here, but I must stress you can call it whatever you want. If you want to call it Bazooka Jim, if you want to call it Miss Kitty, you're welcome to do that. It's just that I'm calling it C in this definition for the sake of convenience. And a positive integer constant. Integer constant. And 0, so this is, let's say, numbers like 1, 2, 3, 4. It can't be 0. It's a positive integer. So we're going to call it n0 such that for all n greater than or equal to n0, it has to be that f of n is less than or equal to c times g of n. So sometimes when people describe this to you, sometimes people use the phrase f is Big O of g. Some people will say is in as opposed to is. There's a meaning and reason for that. Some people also say f is order of g. But So let me give you an idea what I mean by this. So in the plain language, let me just draw you a picture. I'm going to draw you two pictures. They're going to be kind of cute and small. So these are a couple helpful pictures for this. So imagine that I have a linear function. Ooh, that was a little squeaky. We have a linear function here, and I have a quadratic function like this. I could draw straight lines. I know, right? Amazing. So suppose that this is f, and this is g. And suppose I have another function here. Say, I don't know, one that kind of wiggles around a little bit, and then goes like this. Does the wiggle, okay? And then I have another function that goes like this. And suppose we're considering as the input gets large. So let me just get out of the way here. So I have f and g. So I have this first picture here. So anyways, we have f and g here. And as n gets large, you're going to notice if I look at my first picture, if I look at the line that, this parabola that plots out g of n, notice that everywhere I look on here, notice everywhere after here, regardless if I start at 1, 2, 3, 4, 5, so on and so on, notice that the g curve always is above the f line, right? That's always the case. So notice that in this case, if I were to look at this function, it wouldn't matter if I were to make, say, C1, 2, 3, 4, 5, 6. But notice that I could imagine this just being one function times some constant. And everywhere after, say, 1, everywhere after this, if I look just after this line, every time C times G of n is always going to be larger, it's going to dominate F everywhere after this. So notice that this line, this curve is always going to be above the line. Something similar happens over here. Just to be a little bit clear, I'm going to call this C times G of n. I don't really know what C is. I'm just drawing you a fun picture. So notice here that for smaller values, the F curve goes above the G times C curve. Does everybody see that? Just for a little bit, right? But notice that after that point, presuming that these are the behaviors of these functions afterwards, so this one keeps going up this way much quicker than, say, this F curve does. If I do that, notice that if I look at this point where these two intersect with each other, notice I can pick here or anywhere after here, and notice that this curve, the G-related one, is always above the one with the F. So just to keep this dramatic for you, let me grab my pointy sticks. Okay, that was a little loud. I shouldn't do that right close to the microphone. So if I look at this, notice that everywhere after n0, my one right here always stays above the one to the right. That was brutal. I'm sorry. But I could do the same thing here. Notice that everywhere after the top one, it never goes and crosses ever again. That's the big thing. And yes, I'm coming in for like a fatality or something here. So anyways, so this is just so the key things I want you to identify from this definition are that the game is simple. And I usually like to call it the game plan. Is notice that the definition says that there exist these two constants, the C, and this positive integer constant n0. So as long as these two constants exist, such that they satisfy the following property, meaning that this inequality holds for all n greater or equal to n0. So after that point that we've identified, which keep in mind it could be that point or anyone after it, say for example my two pictures, keep in mind, these are not proofs or anything. They're just examples. I didn't even define what the functions were. You just sort of look at the behavior and we made presumptions about them. But notice that everywhere after the line where I put n0, it would be the case that this inequality would hold under our presumptions. So just remember, the game is as follows. You got to find this constant and this constant. You got to find those two such that f of n is less or equal to c times g of n for all points after and including n0. So you get to pick these two constants. Sometimes they exist, sometimes they don't. If they don't exist, then most certainly, based on the definition, what I just said, it can't be that f is big O of g. So I thought I would show you just a couple of ways people use big O notation. But are there any questions about this definition? Keep in mind, I'm going to do some examples actually using this in a moment. I just want to show you a couple of use cases, so like how you'd use this notation. And I must stress that I will be going through other asymptotic notations as well. And also I'll be showing you some other techniques that normally in, say, a typical CS class, you will not have enough time to go through thoroughly. So I tend to like to show some of these beyond that. So you might find some of these little, I wouldn't call them necessarily tricks, but most certainly properties that asymptotic notation have. Some of these you'll find very helpful if you're finding good like shortcuts for doing calculations. So anyways, if there aren't any questions, I'm going to proceed to talking about usage. So let's get in on this, okay? Oh man, that was loud. I shouldn't do that right in front of the microphone. So let's let me talk about a couple ways that people typically use big O notation. These aren't the only ones, but I'm only going to be talking about, again, like I said, within the context of algorithms analysis. So say, for example, in like analytic number theory, you might use these slightly differently. But each one, I would argue, has its own place for how you might use it. So a first example I would like to do. So I'll just go 2 common usages. So the first one is in terms of set theory. This is the one that I usually recommend if you want to get a feel for how, you know how I talked about how these functions organize themselves like in the buckets. Now the neat thing about big O notation is that it isn't just simply separate buckets like this. It's actually that buckets nest within each other, as I'm going to show you in a moment. So the first thing is that some people very often write, when you say f is big O of g, they might use what we call the set theoretic in. So they use this symbol. It's a set theoretic in. They might say f is big O of g. Or they might write the n here. That's okay. Like I said, that's just to specify the inputs. So the big thing is that big O notation represents a set of complexity functions. Okay, so let's see. So just for those that are savvy with set theory, I'll just give you an idea of what I'm talking about. So if I write big O of g of n like this, the definition of big O actually says that a function is big O of g if and only if it has those 2 constants, right? That means that for any one function f, you can actually define it as a function or complexity function that sits inside of this set. Think about it, it's just a bucket that contains all these functions. So it contains any one complexity function f such that there exists, this fancy backwards e represents there exists. So it's just an abbreviation for our purposes, but it's just some logic for us. So there exists c, that's a positive real number. This plus just simply means positive. This blackboard R means real number, or set of all real numbers. And there also exists n0, which is a positive integer. We already had that discussion of what that means. For all is an upside down a, so this just means for all. So I may as well just write there exists here too. For all n greater or equal to n0, from your purposes, you'll most likely look at this and say, oh, this is just like an abbreviation of what I was talking about, which is true. For all n greater or equal to n0, it has to be that f of n is less than or equal to c times g of n. And I ran out of space. The squiggly is the closing of this set builder notation. So any function that has these two constants such that f of n is less or equal to c times g of n for all n greater or equal to n 0 will belong to this set. So, for example, if once you get some examples seeing how to prove big O statements, you'll see very quickly that, like I said, they nest into each other. There's other ways asymptotic notations do behave, but big O is always about containment in one direction. Some people would describe this as what we call an asymptotic upper bound. And that's very often how I'll pragmatically describe big O notation to you. It's asymptotic upper bound. So for sufficiently large value of n, it has to be that regardless, it'll always be bounded by a multiplicative constant times the function. There always will be such a value such that this inequality has to hold. So we're just not really caring about a multiplicative factor on that function, g in this case. So let me give you an example of what I mean. So consider the function just where the whatever it does, it outspit 1 always. So this is an example of a constant function. Likewise, you can have functions like 5. You can have a function that spits out 10 every time. It could be some constant c. So it could be any positive real number, for example. These all, you can actually show, using this definition I gave you over there, you can show that all of these are big O of 1. So these are the set of all constant functions. So usually in the analysis of algorithms world, whenever we talk about time complexity, we'd refer to this as constant time. But you'll notice that you can keep doing this. So notice that this right here will contain other functions too. These are just examples. There's more functions in here. But you can also show, for example, that say a function like, I don't know, n, and say 2n plus 5, and say 1000n. All of these are big O of n. So they all nest like this, like a Russian nested doll. So you can keep doing this with different classes of complexity functions. And there's more of them out here. I'll discuss some of those in a moment. So having an intuition that a complexity, so you think of big O as a set of complexity functions, it's meaningful in the sense that if ever you give me a complexity function and you can show me it's out here but not inside here, this separates two different groups of functions, right? So this separates the linear functions from the constant functions. And there's other ones that sit in between these two sets, such as the logarithmic functions. So another usage that you have with big O notation is, and this is one that's very common, and this is a very common convention, by the way, is that some people will write f is big O of g using an equal sign. So I must stress that this is not an equal sign. It just means is. It's not equals, just to be clear. I know it's kind of confusing because that's an equal sign right there. But it's a convention. Like I said, some different areas adopt conventions. This one's actually a useful one. So this one right here is actually because very often when we want to simplify complexity functions, asymptotically speaking, we would like to have some way that we can group terms like in an algebraic way, such that I can discern out the stuff that's mostly fluff, that I can suppress that all inside of a big O, or I can even group big O terms like I'm manipulating algebraic terms. So this is more, I would argue, it's useful for simplifying calculations. So I'll say useful for simplifying calculations. And the biggest thing you need to be aware of is when you use this notation, you read everything from left to right. It's not a true equal sign. It doesn't mean equal to. So this is not like if you're talking about sets here, for example, like in our first usage, you would not use the equal sign in the same way. This would mean literally we're talking about sets. Like we're saying this set is equal to that set. This one is actually saying, hey, look, we're saying that all of this is big O of this. And very often the usage is that you operate it like algebra, but the thing is, you can't just simply just go backwards. You always have to go from, once you start throwing the big O in there, you never can bring it back, because now you're talking about potentially other functions that are sitting inside that big O. It's sort of like it's like a snowball rolling down a hill, and as it collects up these big O terms, now you're talking about more and more stuff, and you can't really discern what you originally grouped in. I'll give you an example of what I mean by this. So this should be read left to right when you use this. So for example, say if I give you f of n, and I say this is 6n cubed plus 20n plus 8. So a couple quick tricks you can talk about when it comes to big O notation is that whenever you have multiplicative constants, you normally can just drop those. So for example, if I have 6n cubed, I can for example talk about I could drop that 6 right there, and I could get a big O of n cubed. So for example, if I have 6n cubed, then I could rewrite that as big O of n cubed. Likewise, I have 20n right here. I can drop the 20 and I could just write n. But remember, I have to put the big O there. And 8, remember, we established those are all in big O of 1. I can replace that with big O of 1 if I wanted to. But you'll notice that I'm always, whenever I do this, I'm simplifying by grouping them into all of these other ones here. And I must stress that these steps are technically not valid unless you define the big O notation to have addition and all of these other things. So some people would call this an abuse of notation, because now you're playing around with sets like they're numbers. And I must stress that not the kind of numbers that you can easily manipulate as sets. So some people, you can formally go about this, but most certainly in the way people use it, it's very much a quick, fast and trick way of doing things. So for example, I can replace the 6n cubed with a big O of n cubed. I can replace the 20n with just an n. So I'm going to write big O for each one of these. They're going to suppress those constants. And remember, I'm just going to look at what the most dominant term will be when I look at this, because I'm trying to figure out the asymptotic order of the functions. So I can have plus big O of 1. So notice that if I tried to go backwards on this process, if I tried to make this like, oh, that's 6n cubed, notice that you can't just simply pull that out, because now what you're doing is now you're talking about any one of the functions that's sitting inside of this set, which it gets a little confusing if you try doing it that way. So do you see why you have to go left to right? Because remember, what big O of n cubed means is that also contains things like 8n cubed plus n squared plus 5, right? I can't just simply replace 6n cubed with that. They're not the same thing. Now, truly on an asymptotic level, it doesn't make any difference if you're trying to determine the big O, but most certainly, it's almost like I said, a snowball effect. As I'm going, I'm suppressing all of those irrelevant details as I'm doing these calculations. So notice here that the most dominant of these functions is the one with the largest exponent here. So I would just simply say that all of this is big O of n cubed. Now you might ask, Dan, why would you have this example here like this? Well, the reason why this usage is rather helpful is because you can imagine that you're counting up all the operations of your algorithm, you're formulating your complexity function. Say these are 3 parts of your algorithm. Say this is the first phase, that's the second phase, this is the last part, the little bit of cleanup. Well, then what you could do is you can separate each one of these, compute the big O of each one, and then you just add up all of those operations in terms of big O. This is very often how this gets used, and you'll find very quickly that when you deal with very big, complex algorithms, when you have lots of bits and pieces, sometimes they interrelate with each other, so you have to be very wary when you do things like this. It could be a little sloppy, but if you have 3 distinct phases where like this thing happens, then this thing happens. Say, for example, an initialization phase, then you have like a nested loop, and then you have something where it does a little bit of a tidy up, say some number of operations, but it just simply returns whatever the result is. That would be something like this. So anyways, just as a reminder of where we are, I gave the definition for big O. I gave us an idea of where we are. So right now we're not analyzing algorithms. We're looking at the big O definition. We're going to see if I give you some function we call a complexity function. I want to know that f is big O of g, but I need to be able to give you some way to verify it for yourself, which is the best way of doing this is a mathematical proof, which at first it sounds really kind of You'll be like, ah, math, oh, that dreaded M word. I assure you, the cool part about this is that if you make a claim to somebody, I'm giving you the way you can reason to somebody about why this thing is true. That's the power of a mathematical proof. It gives you the why answers. It gives you the big W. It's a win and a why. So, anyways, the game plan here is we're going to find these two constants, c and n0, but it has to be that when we pick these two constants, that this inequality right here has to hold for all n greater or equal to n0. So I must stress that a very common pitfall students fall into is they just sort of presume that if they find n0, that everything after that always behaves a very specific way. Meaning that they could just plug in whatever they pick for n0 into this inequality here. So they put in n there, and they say, oh, I'm all done. I'm all done. I don't have to do anything else. And the big problem here is that that isn't actually what this says. This says this inequality has to be true for all n greater or equal to n0. So it's actually a stronger statement than just saying that there exists an n0 such that that inequality works. You have to be a bit more careful. So often the mistake made here is that if you do something like that, you fail to justify why the inequality is true at that point and afterwards. Just like on our pictures over here. It's not just true at this n0 point, it's true everywhere after that, that c times g always dominates f. So let's talk about some functions. Let's get in on this good stuff, okay? So I want to give you some of these different categories because normally when people talk about complexity, they sort of break them into these buckets. These aren't the only ones, by the way. There's some really fascinating ones out there. So let me talk about those. So I'm going to call these common classes of functions. Common classes of functions. So the first one that we actually talked about, this was Big-O of 1. So this is the set of all constant functions. So these are constant functions. So things like 5, 10, any positive real constant c, these are all constant functions. Then you have your logarithmic functions, for example. That m looks a little sad. It's about to turn into an n. It wants to n itself. Oh, that's bad. Anyways. The next we have Big-O of n. That's linear. Then we have Big-O of n log n. This is sometimes called log linear, but most people, if you ever talk to them, they'll just say Big-O of log n. Or sorry, Big-O of n log n, sorry. Most people don't call it log linear, but I've seen this term used for this. I was trying to find a label for you to describe it. I've usually seen this literature discussion when you talk about some very narrow data structures kind of research out there. Some people want to have some way of describing this too without saying Big-O of n log n. There's Big-O of n squared, so you might recognize a lot of these names if you've studied functions before. We have quadratic functions. So like I said, remember, these are sets of functions. So for example, like quadratics here contain things like 5n squared plus 5. Those are all quadratics, right? So other ones also include polynomials. So we have n to the c. So Big-O of n to the c, these are polynomials. So this is for any constant c greater or equal to 0. So this subsumes a good chunk of those up there. In fact, it technically consumes every single one of the ones up here. So you can actually look at this as successive nestings of functions. So Big-O of 1 is contained within Big-O of log n. Big-O of log n is contained within Big-O of n. Big-O of n is contained within Big-O of n log n. Big-O of n log n is contained within Big-O of n squared. Big-O of n squared is contained within Big-O of n to the c, where as long as this is some constant c greater or equal to 0. So you can pick the c to be whatever you want. It's some constant. So it can make it 3, and then now you have the cubic functions. And then you have some other things like exponential functions. So you have big O of c to the n. So this is exponential. So this is any constant c greater than, well, c greater than 1. I was about to write 0, but that doesn't make a whole lot of sense. It's an exponential function. Yeah, c greater than 1. So this is stuff like 2 to the power of n. The things that grow rather quickly. There's some other ones too, like there's big O of n factorial. These grow faster. And there's also other things out there, some that I don't even know what they're technically called in the literature. Just normally, if you ever had an algorithm that ran this slow, you'd kind of throw it out unless your problem was really that tough. Things like big O of n to the n. I'll call it oops, okay? So anyway, so these are some common classes of functions. Normally when we talk about f and g, g is normally the function that would be sitting inside of one of these. So normally we'd like to characterize them like these, but I must stress that there's other functions too. There's some that are so strange that it's very hard to explain them to you with only a matter of one sentence. Some grow so slow, for example. There's something called the log star or iterative logarithm. For example, log star of n. For all practical values of log star n, this grows so slowly that in practice that it may as well treat it like a constant for practical values of the input. There's other ones even out there called, for example, like the inverse Ackermann function, that for up to about, I can't remember the number off the top of my head, they grow so slowly that in practice, if you were to talk about, say, 1, 2, 3, 4, 5, the numbers are still going to be so small that if you get up to, say, 10 billion, it's still going to be a number that's not going to be anywhere close to the, or even, it's ever going to exceed the number like 4 or 5. So when you get things like the inverse Ackermann function or log star, which are other functions out there, they appear in some data structure analyses, such as disjoint sets. They grow so slowly that, but they're not as common as these ones. That's why I'm focusing on these ones. That's the point I'm getting at. Is that there's a lot more categories out there than just these ones, but these are the ones that if you talk to anybody in computer science, most people will know about these ones.